Hi everybody, and welcome to Lesson 1.2, Scientific Method and Environmental Math. The content in this video is aligned to the third edition of Environmental Science for AP and covers information from College Board Science Practices 4 and 6. Being able to understand and work effectively with environmental science requires that we have a clear understanding of the components of an appropriate research experiment and that we have the clear ability to utilize quantitative skills to understand data. This leads us to the content objectives of understanding that analyzing research studies that test environmental principles is important, and we should be able to apply quantitative methods to address environmental concepts. By the end of this lesson, you should be able to explain the difference between experimental and observational science, identify the steps of the scientific experiment, identify and define the major parts or components of a scientific experiment, identify a testable hypothesis or scientific question for an investigation, identify a research method, design, and/or measure used, describe an aspect of a research method, designed, and/or measure used, determine an approach or method aligned with the problem to be solved, apply appropriate mathematical relationships to solve a problem with work shown, specifically in dimensional analysis, and calculate an accurate numeric answer with appropriate units. Which leads us to being able to answer the guiding question: how do we generate and understand data? There are multiple ways in which we generate knowledge in scientific circles. Clearly, the most common way we do this is through the scientific method. However, we apply this method in multiple ways. Most scientific understanding is generated through one of two applications of the scientific method: experimentation or observational studies, which are also known as field studies. Experimental studies are often seen as the gold standard of scientific research. This is because experimental studies are most often completed in a laboratory setting and can be controlled. This allows for a clear understanding of whether or not there is a clear relationship between variables being studied. While experimental studies provide a more specific and detailed understanding of how the variables are related, it is sometimes difficult to apply these concepts to the real world as the variables are not so easily managed. Observational or field studies are different in that they take place in the natural conditions or the natural environment. This kind of study provides a clear understanding of how the phenomenon occurs in the real world. We can see how the various variables and conditions interact and work together to produce the effect that we see. While this kind of study is effective for seeing real-world events, it is difficult to identify clear and direct connections between variables because of the variety of interactions. Each method of study has its merits and should be selected based on the kinds of variables being studied and the ultimate outcome of the study in terms of generating scientific understanding. Most of you have been exploring the scientific method since elementary school. What you see here is a more complex and scientifically accurate model of the scientific method as it is applied by practicing scientists. Your traditional understanding of the scientific method is most likely make an observation, ask a question, pose a hypothesis, design an experiment, take data, and make conclusions. While this isn't necessarily incorrect, it skips over very important components of the process that are vital for true understanding and communication of scientific knowledge. One of the most important things to understand about the scientific method as we use it is that the understanding that true scientific research is iterative and recursive. It is not a linear process, and it requires that assumptions, questions, and hypotheses be revisited and revised throughout the experimental process. All applications of the scientific method begin with the making of observations and the asking of questions. However, it is not effective in true scientific exploration to go immediately into the developing of a hypothesis and an experiment. First, it is vital to do background research on the topic or question. It is likely that the question has already been answered, or that information exists that can help inform or shape the development of a hypothesis or experimental method that better answers your question. After background research, hypotheses can be developed to help guide the experimental process. In the past, you may likely have been told that a hypothesis is an educated guess that is written in an if-then format. Unfortunately, this is too simplistic and conflates two important components of effective scientific methods. For our purposes, a hypothesis is an explanation of a phenomenon. You are attempting to provide an explanation for what relationship, if any, exists between variables under review. There are two types of hypotheses. A null hypothesis, which indicates that there is no relationship between the variables being studied, and an alternative hypothesis, which indicates that there is a specific relationship between the variables and which attempts to define that relationship. The null hypothesis is identified by the notation H sub 0. Alternate hypotheses are identified by the notation H sub 1. All experiments have a null hypothesis, even if it is not explicitly stated. Once a hypothesis has been articulated, it is possible to develop a prediction. These are directly testable statements that are in the if-then format. The use of predictions helps to clarify both the variables and the expected relationship between them as it relates to the experiment itself. While it may seem pedantic to separate predictions and hypotheses, they are two different things. Remember that there are two major types of scientific studies. A control is almost exclusive to laboratory experimental studies, and it is very difficult to have true controls in an observational or field study. Controls are variables or conditions that are kept constant throughout the entire experiment. This is to ensure that the relationship being explored between variables is due to an actual relationship between them and not other factors. Speaking of variables, there are generally three types that are included in an experiment: independent, dependent, and external. Independent variables are those that are manipulated or changed by the investigator and are thought to cause a change of some kind, whether direct or indirect, in the system being explored. The dependent variable is that which responds to the changes in the independent variable. It is the one that is being measured. External variables are those that are likely to affect the outcome of the experiment, but which cannot be eliminated or controlled. Laboratory experiments seek to reduce these external or confounding variables as much as possible. Lastly, experimentation often uses the inclusion of groups to study relationships between variables. An experimental group is one that is designed to determine if there is a relationship between the independent and dependent variables. The experimental group is the one that is treated with the independent variable to measure the response. An experiment can have more than one experimental group. The controlled group, not to be confused with the control, is one that is held constant. That is, it is kept as close to natural conditions as possible so that comparison is available with the results of the experimental group. Scientists will then determine the most appropriate method of experimentation based on the hypothesis, variables, and the question being researched. Modifications can be made to the procedure if needed as the data is collected. Data is compiled and analyzed through graphical, tabular, or other mathematical means to determine if a particular relationship between variables actually exists. The kind of analysis will depend on the kind of data collected and the way in which it was gathered. Conclusions for scientific experiments indicate which hypothesis was supported. Remember, you will never prove your hypothesis in any way. You can demonstrate that the evidence indicates that this relationship is the most likely explanation, but you cannot prove it. The appropriate language should be supported or rejected. Lastly, good science is communicated to others with the expectation that fellow scientists will attempt to replicate your results to determine if your conclusions are valid or not. Let's walk our way through an example. Imagine a university professor teaching an 8 a.m. biology course. Over the first few weeks of the semester, the professor gives 3 tests. But she's frustrated because a group of students always arrives late to class, and they always have coffee with them. However, when looking at the scores for the tests, the professor sees that the students who are often late have done better than students who are on time. She wants to know if there's a connection. The professor creates a hypothesis that because caffeine is a stimulant and wakes up students, this is why they're doing better on her tests, even though they are late to class. However, she understands that there may not be any connection at all. Therefore, her null hypothesis is there is no connection between lateness and test score. Her alternative hypothesis is coffee wakes up late students, so they do better on the test. The professor predicts that if students consume caffeine before a test, regardless of their attendance on time or being late, their scores will increase on the assessments. In designing her experiment, the professor identifies her variables and groups. She understands that there are various conditions that she can manage and in various conditions that she cannot. She chooses to provide the same type of test to all students at the same time and after using the same teaching method. However, she understands that students may come to class unprepared, be having a family or health crisis, experience stressors like traffic, or have other problems that may impede their ability to be successful on the test. She identifies the variables of interest as the consumption of caffeine, its presence or absence, not its specific amount, as the independent variable, and the test score as the dependent variable. Lastly, she divides her students into 2 groups, one that will be allowed caffeine before test, and one that will not. After breaking her students into the 2 groups, the professor teaches 3 new sets of concepts to students in the same way that she had previously. Then she gives all students the same tests. This is to make sure that she isn't inadvertently giving one group of students a test that is harder or easier than another. She then repeats this process 3 times. At the end of the experiment, the professor looks at the data across all of the tests and at the tests individually. She was very careful not to look at the data between tests to avoid introducing any bias in her teaching method. Overall, she notices that the caffeine group has a score that is 5 percentage points higher than their non-caffeine peers. However, when she looks at the individual tests, she sees that several of the caffeine group perform significantly better than their same group peers. She identifies these students as outliers and re-evaluates the data without them in the calculation. When this happens, she notices that the average difference between the groups is only 3 percentage points. After evaluating the data, the professor determines there is not enough evidence to make a valid conclusion. She may indicate that this is because the outliers skewed the results toward the caffeine group, or that the sample size was too small to provide an adequate data set, or that the exclusion of the outliers made the difference insignificant. All of these are valid conclusions or interpretations of the data that she generated from her experiment. Based on any of these, she would determine that the null hypothesis was supported and the alternative hypothesis was rejected. Based solely on her data, there is no difference between consuming or not consuming caffeine before a test as it relates to the final score. Now, one of the most important skills that is needed for success in AP Environmental Science and in scientific experimentation in general is the ability to accurately select and apply mathematical skills to data sets. In AP Environmental Science, you are required to use dimensional analysis. This is also known as the factor label method, and many of you are familiar with it because of chemistry and stoichiometry problems. You will apply the same practices here. When the term work is used in relation to math problems in AP Environmental Science, it refers to the clear setup using dimensional analysis. It does not mean your long division or multiplication work. In many cases, questions on the AP exam, particularly in the FRQ section, Math questions are worth 2 points. 1 point is awarded for correct setup in dimensional analysis, and another for correct answer with units. Make note of the following. A correct answer without dimensional analysis setup will receive 0 points, regardless of the point value of the problem. A correct answer without units, regardless of setup, will receive 0 points for the answer. A correct setup but an incorrect answer may receive partial credit if the question is worth 2 points. An incorrect setup but a correct answer may receive partial credit if the question is worth 2 points. Remember, the last 2 statements only apply if the problem is worth multiple points. Single point math problems are all or nothing. The setup and the answer must both be correct and include the correct units, or no points will be given for that question. You will typically see dimensional analysis style problems as they relate to energy conversions or other simple conversion or factor reducing problems. When you attempt to solve a dimensional analysis problem, keep the following steps in mind. Identify what you know after reading the problem. Identify and list any conversion factors that you may need. And identify what you have been asked to find, including final units. There are very few things that you will need to clearly memorize in this class, but the metric scale is one of them. You should know how to convert across the entire metric scale from tera all the way down to milli. These conversions will not be given to you in any problem. You should also know how to convert inches to centimeters by knowing that 1 inch is equal to 2.54 centimeters. You may also use 2.5 for ease of computation and still receive credit for an answer if the math works out correctly. Let's look at this sample problem. A scientist wants to design a clock that counts down in seconds throughout the day rather than one that counts up in minutes. First, he has to know how many seconds are actually in a day. He knows that there are 60 seconds in 1 minute, 60 minutes in 1 hour, and 24 hours in 1 day. Make note that 60 seconds over 1 minute and 1 minute over 60 seconds are equivalent terms. They mean the same thing, and their orientation is only important based on which unit needs to be eliminated. Our final unit needs to be seconds per day, so we know that on the top, our remaining unit must be seconds, and on the bottom, our remaining unit must be day. Here we identify 60 seconds over 1 minute, multiplied by 60 minutes over 1 hour, and 24 hours over 1 day. We then multiply across the top and multiply across the bottom and remove any redundant units, such as minutes on the top and bottom and hours on the top and bottom. That gives us our final answer of 86,400 seconds in 1 day. Make note that the vertical bars between the mathematical statements is indicative of multiplication. You can write 60 seconds over 1 minute and then use the multiplication symbol of X or dot, and then include 60 minutes over 1 hour, as long as it is clearly identified that you are multiplying across the top and multiplying across the bottom. The following slide provides you with an opportunity to see how some of these ideas are connected together. Feel free to pause the video and explore the connections between these topics. Then use the statements at the beginning to review.